we're going to move on to the next part of this topic, which is all about this concept of impulse. This one's going to be a very small aspect. Now, we've talked about momentum. Now, let's talk about changing an object's momentum. Well, in order to change an object's momentum, it requires us to apply a force for a certain amount of time. This is what actually results in what we call impulse. Note that impulse is represented by the letter J, a capital J, mind you. So if you see the symbol J, that represents impulse. Now, I do want to point out that that's mainly used in the in the context of the Regents physics topic. Remember, at the end of the year, you are expected to take the Regents physics as well. So when you look at the Regents reference table, you will see impulse represented with a capital J on the reference table. You will not see that on the AP reference table. Um, so going back, so an impulse would represent anything that essentially applies a force for a certain amount of time. This could be things like kicks and shoves. Depending on the amount of force you apply or the amount of time you apply it for, could change how much of an impulse you provide to an object. So here's a perfect example of an impulse. Here we have an object that is moving and is stopping. A lot of times, impulse is used to represent things like collisions, objects coming to a stop, crashes, all that type of stuff. Now, an impulse is a change in the momentum of an object. That is something that is important to keep in mind. So, the equation that you have on the reference table, on the AP reference table, is given in black. The change in momentum equals F change in time. So it's just, if you want to find the change in momentum of an object or the impulse, you just take the force and multiply it by time. The reason I'm going over the concept of impulse with you guys, even though the equation doesn't appear with the symbol J, is sometimes the AP does actually use the word impulse, and you have to recognize, oh, that is the change in momentum. Now, the Regents reference table basically has this exact same equation, except it adds in this blue part with J equals delta P equals F delta T. Again, hitting home that the impulse is by definition a change in momentum. Impulse and change in momentum go hand in hand. So if you apply an impulse of a certain amount, you're changing the object's momentum by a certain amount. Think of impulse as essentially being work, and momentum is the energy. So when you do work, you change an object's energy. When you do an impulse, you change an object's momentum. They go hand in hand. And then this part, this part, the m delta v, this is what I call the extension to this equation. Now, a lot of times when you're doing these problems, you're not just going to be given force and time, you're sometimes going to be given mass and velocity. Now, what you could do is figure out what the momentum is using those two masses and velocities. You could find the difference of it and then use the equation to do F delta T. Or what you could do is combine the two equations together into one so that you do one single step. So if you want to make your life easy, you can add on this extension to the equation and basically say that because the change in momentum would just be mass times your change in velocity, that F times delta T equals M delta V. Now, one thing that's pretty interesting about this equation is if you pay attention, if you take this delta T and divide it over to the other side, you have M delta V divided by delta T. Now, if we look back to our other equations, delta V divided by delta T is acceleration. So we end up getting mass times acceleration. F equals ma. The concept of impulse really is just Newton's second law. All right. Now, coming back, I did want to point out that this is actually the reason why I said that momentum could be represented with the units of Newton seconds, because of the fact that change in momentum, aka impulse, is force times time. I could also use force times time as my units. However, weirdly enough, you normally see this in the context of being used for impulse, and then momentum would switch it back to kilogram meters per second. So sometimes you might see a question saying, "Hey, we give an object an impulse of 20 Newton seconds. What's the change in momentum?" And you have to recognize that it would be 20 kilogram meters per second, because again, Newton seconds and kilogram meters per second, they go hand in hand. Impulse, change in momentum, same thing. You'll see a few examples like that, though those types of questions come up more so in the region stuff. Now, there is one concept that we need to be able to cover for impulse, and it's pretty much related to the inverse nature of force and time. So let's consider the case where we are driving down in a car, right? Which one's going to hurt more for the car or for us driving the car? Crashing into a wall or crashing into a stack of hay? Now, if we consider two different cars crashing into these two items, uh, let's assume that the two cars are identical. They're traveling with the same initial speed and they have the same initial mass, or just same mass. When they come and crash and they come to a stop, both of the cars will have this exact same impulse because they start with the same momentum, same massive velocity, and then they'll both end with zero momentum. So their impulse will be the same. However, what's going to be different is the amount of time it takes for the car to come to a stop. In the case where you crash into a brick wall, the time for the stop will occur very quickly. So the time will be very small. Likewise, crashing into a big pile of hay will result in your car coming to a stop over a much longer period of time. Because of the fact that the impulse is identical, that means that the car that comes to a stop very quickly with a small time will experience a much greater force. On the flip side, the object that took a lot longer to come to a stop would end up experiencing a much smaller force. This is actually one of the reasons why airbags are installed in cars is in order to prolong the time it takes to come to stop. The longer the time can be taken, the less force is needed to bring us to a stop. That's basically the idea of impulse, and it's a major, major concept to keep in mind. This idea that increasing time decreases the force and vice versa. So it's not the speed that you hit the ground with that ends up hurting you. It's the amount of time it takes to stop and to stop that speed when you hit the ground. If you hit the ground on concrete, it's going to hurt a lot more than if you came and hit grass or dirt or a giant pillow. Because in those other cases, the time that you take to decelerate is going to be very long. So the time is very big, meaning the force is going to be very small. All right. Now, with that being said, let's do a few practice questions. So pause video, work itself, and we'll go over in a second. All right. So here we go. They give us some information. They give us the mass. They give us the time, and they give us the initial speed, or they give us the initial and the final speed. And they want us to figure out the average force. So, like I said, we can take the impulse equation and combine it with the extension to the impulse, m delta v. Again, this is just me going delta p, the change in momentum, and just jumping straight into the equation for momentum. So if I take these two numbers, making sure to convert my 1 milliseconds into seconds, I end up getting that the average force is 3,500 newtons. Now, one thing to keep in mind is that in a lot of these questions, they will talk about average force because one thing to keep in mind is that in a lot of these cases, the force will kind of build and decrease over the time. It's not like a static force. However, we can pretty much almost consider as if it did do that. If you actually look at data of car crashes, you'll actually notice that the force will actually peak and recede within a certain time period. But what matters is what the average force is during that time. All right. Here's the next question. Pause video, work itself, and we'll go over in a second. All right. So once again, they give us the mass, the speed, and they give us the time. So we just plug it in to the equation. Well, to find the impulse, again, it's just the change in momentum. So I could just figure out what the initial momentum zero. I could figure out what the new momentum is, and we end up getting that the impulse is going to be 12 Newton seconds. Now that I have the impulse, I can combine this into the impulse equation to figure out what the force is, divide this by 8 milliseconds. Again, remember to convert, and we get 1,500 units. All right, here's the next one. Pause the video, work itself, and we'll go over in a second. All right, so we have the stuntman jumping out of a window. They want us to first figure out how fast he's falling when he reaches the ground. I could do this one of two ways. I can use conservation of energy, or I can use kinematics. We'll start off with, we'll just do kinematics since that's one's easier. We know what the distance is, we know what the acceleration due to gravity is for objects that are falling, and we know what its initial speed is 0. So we plug this up and we get that the speed that they reach the ground with is 30 meters per second. Now, if they land in a large pillow and it takes 1.5 seconds to come to rest, I can use the impulse equation, plug the numbers in, and figure out that the force is going to be 1,600 newtons. If instead they land on ground and come to rest at 10 milliseconds, well, we can see that changing the time results in the force being 240,000 newtons. So again, you can see how drastic the force ends up changing, and it explains why landing on solid ground is going to be a lot more dangerous because hitting into this target, this pillow, basically extends the time, decreasing the force. This is again the main concept to keep in mind: the inverse nature of force and time when it comes to the impulse. This will be the last one, so I'll pause the video, work itself. I'm going to go for a second. All right. So nothing really changes. The only difference is that we have two speeds. So when I go to plug in my impulse equation, I just take the difference of 4 to 8. Since they're going in the same direction, I don't have to worry about any signs. So difference is 4. Plug the numbers in, and I get a force of 60 newtons. There's a few more practice questions, but they are all pretty much the same. We'll go over the rest in class. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.